In this video, we'll be discussing the integral test. The integral test is a test that is specifically used when three details occur. So we can make a conclusion of a series will converge or diverge in comparison to the integral of that same function. So if I have a series of k equals 1 to infinity of a sub k, and I can compare this a sub k to the integral instead of 1 to infinity. Again, notice the bounds are actually the same in terms of some other arbitrary function f of x, then I'm going to be able to compare the convergency of this in regards to the convergency of this, assuming, and again, we don't really make assumptions in calculus, so we have to prove three qualifications. Number one, that the function f of x is continuous. Number two, that the f of x function is always positive. It'll throw things off if it's not. And number three, that it is monotone decreasing, meaning that it's never actually going to be increasing. So if we can prove that f of x, where f of x is in some way equal to a sub k, if we can prove that that function f of x is both continuous, always positive, and monotone decreasing, then if this integral converges, then so does this. If this integral diverges, then so does this. So this will allow us to conclude that both the summation a sub k and the integral of f of x dx will diverge or converge. So this is the only real test that we've been looking at where we can actually determine in a comparison that if one of these things does something, then so does the other one, and vice versa. So let's go ahead and apply this integral test. So the first example of the integral test is the summation of k equals 1 to infinity of k over k squared plus 1. So again, before I can even apply the integral test, I have to first work out the kinks of the function. So let's start by looking at f of x. So I'm going to go ahead and convert this to f of x equals x over x squared plus 1. Now, the reason why we converted over the x functions where we don't actually work in it in terms of k is because, again, remember, k actually focuses on the concept that we're only plugging in values that are whole numbers, ignoring 0 sometimes, while this is plugging in every value. So we want to integrate this function, and we want to evaluate whether or not the series will converge. So the way we're going to do this is, number one, we're going to check that this thing is always positive. And it is, because based on the bounds from 1 to infinity, the values in here will always end up being positive. Okay, so that's checked. Number two, that it's always decreasing. Sorry, always, we should have done continuity first. And this function is continuous everywhere. Well, the denominator doesn't actually have any locations of error. It would if this was an x squared minus 1, but because it's x squared plus 1, it doesn't actually have any issues. So it is continuous everywhere. It is positive always. And then we just have to figure out, is it always decreasing or always increasing? Or is it doing something in the middle? Well, the way that we can check that, that's 2, that's 3, is by looking at the derivative of this function. By checking the derivative of the function, we will be able to determine increasing or decreasing. So if we look at the function and determine that it's always negative, then we can conclude that this thing is always decreasing. So there's no issues. Let's go ahead and then take the derivative of this thing. If I use the derivative on this function, I'm going to go ahead and end up doing a quotient rule, such that I end up with something that looks more like this: 1 minus x squared all divided by x squared plus 1 to the power of 2. Now, the key part about this is that the denominator is always positive, but if you look at the top here, any number that I plug in, I'm supposed to be plugging in numbers that are larger than 1. So if I plug in 1 here, I'm going to get 0 on top. Well, this said it's got to do monotone decreasing, which means that it's not always decreasing. It specifically refers to that it's decreasing with potentially never increasing. So with that statement being made, this thing can be constant. So if the change is 0, then yes, this is retaining constant on the first term. But the minute I start plugging in new values, this x squared value will be positive, but there's a negative in front of it, and that value will always be larger than 1 from this point forward because I'm plugging in values larger than 1 as whole numbers. So this right here implies monotone decreasing. Check. So now that those three pieces are identified, it is continuous on the bounds that we're working with, 1 to infinity. It's always positive on 1 to infinity, yes, and it's got a monotone decreasing setup from 1 to infinity. So then I can apply the integral test. Apply integral test. And again, I abbreviate int INT. So I'm going to apply the integral test, and the integral test is specifically saying that the integral from x equals 1 to infinity, the exact same bounds that I started with up here, of the function x over x squared plus 1 dx. If I can evaluate this and get a number, then this original series will converge to something. If I evaluate this and I don't get a number, I get to say infinity or negative infinity, then this thing here will diverge. Well, remember that this is an improper integral and we can never actually set these things up. So it's the integral from, b to infinity of the integral from x equals 1 to b of x over x squared plus 1 dx. We can use a u sub on this, u equaling to x squared plus 1. My du is going to then be equal to 2x dx. I need a 2 here, therefore I'm going to put a 1/2 on the outside. I'm going to evaluate, again, one more time, the integral before I evaluate the limit. So it's the integral, or the limit of b goes to infinity of 1/2. The integral from x equals 1 to b of this thing then changes into 1 over u du, which is going to provide me with a natural log, technically with an absolute value, but because all the values are positive, I don't need that absolute value. I'll say that one more time. Because I'm evaluating this integral, and this integral is the natural log of the absolute value of u, with x always being positive and x squared always being positive, this thing transitions into the limit as b goes to infinity of 1/2, the natural log of the absolute value. But the absolute values are not necessary to write because x squared plus 1 is always positive, no matter what I plug in, because I'm going from 1 to infinity. So there shouldn't be any issues with this. So evaluating from x equals 1 to b, as I plug these values in, I will be dropping those absolute value bars. So the limit as b goes to infinity of 1/2 times the natural log of when I plug in b, so b squared plus 1, minus 1/2 times the natural log of the absolute value, again, the absolute value of 2. So as b goes to infinity, this term right here is going to continuously get larger and larger. And if that value continues to get larger and larger, then it's infinity minus a number, which equals to infinity. So by the integral test, we can come back to this thing right here and say, given that the integral from x equals 1 to infinity of x over x squared plus 1 dx equals to infinity, the series k equals 1 to infinity of k over k squared plus 1 will diverge. And that concludes the concept on how to evaluate that integral test. There are multiple examples to this integral test. We'll go ahead and do one more. This next one will be along the lines of the series of k equals 3 to infinity of 1 over the square root of 2k minus 5. So we still have continuity, we still have to prove always positive, and then we also have to prove that it is monotone decreasing. If we can't prove those three things, then the integral test doesn't apply and we can't actually utilize it. So, is this thing always continuous? Well, this function f of x equaling to 1 over the square root of 2x minus 5, it is continuous everywhere except for where the denominator is 0 or where the radical has a negative on the inside of it. But since we're working from 3 and on, 3 never has an issue with this interior of the radical, so it is continuous everywhere. Also note that this is 1 over the positive square root, and the square root will never spit back a negative number. Given that the square root will never spit back a negative number, we are always positive. So the last thing I got to worry about is just, is it monotone decreasing? And again, the way that we prove that is just by taking the derivative of it and checking to make sure that the derivative is always going to be a negative number. So if I rearrange this thing, I'm going to have 2x minus 5 to the power of a negative 1/2. I bring down the negative 1/2. 2x minus 5 to the add 1 to the power, 1/2. And then, I'm sorry, subtract 1 from the power because I'm taking the derivative, minus 3/2, and then multiply by the derivative of the inside, which is 2. You'll notice that I'm going to end up with 2 times 1/2, which cancel each other out. a negative 1 on top, and a 2x minus 5 inside of a square root quantity cubed, because that's what that 3/2 power really is, with a negative in the exponent. So this is really what the function is after I take its derivative, and you'll notice the bottom piece is always going to be positive because it's a square root. The top is going to be negative, and therefore this is always monotone decreasing. If I plug in 3, I'm going to get a negative fraction of some form. So this is us making sure that we can apply the integral test. Now using the integral test, I'm going to go ahead and integrate this function from I'm going to use x equals 3, and I'm going to go ahead and straight up change it to b right now with putting the limit as b goes to infinity out front. Again, it's important for us to make sure that we don't forget to change these things based on their improper integrals, so we might as well go ahead and do it right now. This is then the integral of the function of 1 over the square root of 2x minus 5 inside of a 1/2 power dx. And then we have to evaluate this integral. The way that we evaluate this integral is again by using a u sub. When doing a u sub, we'll do u equals to 2x minus 5. My du is going to be equal to 2 dx. So I'm going to have a multiple of 1/2 in here. As I go through the rest of the steps in this problem, we'll come to the conclusion that integrating this function right here, manipulating, utilizing it, we'll end up getting the limit in the end as b approaches infinity of some form of a square root of 2x minus 5, evaluated from 3 to b. Again, there might be a 1/2 in there or not, but what's important is that this thing here, as b goes to infinity, this thing will go off towards infinity. And if I plug in 3, it's not going to slow it down enough for it to do anything other than go towards infinity. So again, if I evaluate this integral using the appropriate u sub, I'm going to get something that has some form of a radical in it, but that radical is going to be in the numerator tending towards infinity. Therefore, by the integral test, the series 1 over the square root of 2k minus 5 from k equals 3 to infinity will diverge. Again, if this one does, then so does this series.